The root test is a test that determines whether a series is divergent or convergent. It states that if you take the limit of n as it approaches infinity of the nth root of the absolute value of a series a sub n, you will get the answer B. If the answer is less than 1, then the series is convergent. If it is greater than 1, then the series is divergent. And if B is equal to 1, then the root test is inconclusive. Because we take the absolute value of a of n, when we use the root test in an alternating series problem, if the answer comes out to be convergent, it will always be absolutely convergent instead of conditionally convergent. To get the basics down, let's first take a look at this first problem. Sigma from 1 to infinity of 7x over 5x plus 7 to the 5x. Now the first step would be to take the limit of x as it goes to infinity of the xth root of 7x over 5x plus 7 to the 5x. Now that would obviously just be the limit as x goes to infinity of 7x over 5x plus 7 to the 5th. Now, since it's a limit problem, we can first take the limit of the middle and then raise it to the 5th power. So when you just take the limit of the 7x over 5x plus 7, you get 7/5 because you divide every single term in that polynomial, in that fraction, by x. So it'd be 7x, and then if you put it back into the original, then be the limit as x goes to infinity of x 7 over 5 to the 5th, and that would be greater than 1, so the answer would be divergent. Now this is a fairly simple problem because all the terms are raised to the nth power, or in this case the xth power. But if you go on to a different problem like number 2, which is the sigma from 1 through infinity of negative 1 to the k plus 1 times k over 2k. Not all of these terms are raised to the k power, and so this will be a little bit more difficult. And we'll be using L'Hopital's rule in this problem, which I will show you later. So this is an alternating series problem, first of all, because there is the negative 1 to the k plus 1. And so in an alternating series problem, before you start doing the root test or any other test like that, you first have to see that the limit as k goes to infinity of a of n is equal to 0. So there we go over there. And also a of n is decreasing throughout the problem. And you can determine whether or not it's decreasing if you take two numbers and plug them in and see and compare them to each other. So if we take k is equal to 5 and k is equal to 6, when k is equal to 5, it'd be 5 over 2 to the 5th. And when k is equal to 6, it'd be 6 over 2 to the 6th. And when k is 5, the term will be greater when k is equal to 6, so the polynomial or the series is decreasing. Now, so if it's both decreasing and the limit of k as it goes to infinity of a of n is equal to 0, then it's convergent by alternating series test. Now, we're going to use the root test for the rest of the problem. So let's first take the kth root of k over 2k as k goes to infinity. So that would equal the limit as k goes to infinity of k to the 1 over k divided by 2, which you can raise this to the e ln. So this would just be e to the 1 over k ln k if you use logarithmic principles. Now, we're first just going to take the limit as k goes to infinity of 1 over k to the ln k over k. And we'll be using L'Hopital's rule. L'Hopital's rule basically says that if you have the limit where n goes to infinity and the numerator and denominator both equal 0 or infinity when you plug in infinity, then you can take the derivative of the top and the derivative of the bottom separately and then take the limit from there. So since both ln k and k equal infinity when k is set to infinity, then you can take the derivative of both the numerator and the denominator. And I'll be denoting this by using h and then having a circle around it. And so it will become the limit of 1 over k over 1, which will just be equal to 0. So we're going to plug it into the original equation. So it'll be e to the 0 over 2, which would equal to 1/2, which is less than 1. So the answer would be absolutely convergent by the root test. Now let's take a look at one more problem. So it states the sigma from 1 to infinity of 6n to the 4th minus 7n to the 5th over 8n to the 5th plus 4n to the cubed to the nth. So in this problem, we're first going to be taking the nth root of the of a of n as n goes to infinity. So it just come out to be limit as n goes to infinity of the nth root of 6n to the 4th minus 7n to the 5th over 8n to the 5th plus 4n cubed to the n. So that just equal a limit as n goes to infinity of 6n to the 4th minus 7n to the 5th to the 1 over n times 8n to the 5th plus 4n cubed. And so let's set that equal to the limit as n goes to infinity of e to the 1 over n ln 6n to the 4th minus 7n to the 5th over 8n to the 5th minus 4n to the 3rd. Now this structure of setting the exponent to the ln and then taking the e of it is very, very helpful, especially when you still have that little exponent there and you can't get rid of it. And so we're going to be taking the limit of the exponent first, and then we'll be plugging it back in just like we did in the previous problem. So it would become the limit as n goes to infinity of ln 6 n to the 4th minus 7n to the 5th over n, which would equal infinity over infinity. And then using L'Hopital's rule, we would get that it would be the limit as n goes to infinity of 24n cubed minus 35n to the 4th over 6n to the 4th minus 7n to the 5th. Now, since you have all these variables, the same variable going to different values, you can cross out the n to the 3rd and n cubed and all of those terms. So it just become the limit as n goes to infinity of 24 minus 35n over 6n minus 7n squared, which would just equal 0. So we're going to plug this into the original equation. So it's limit as n goes to infinity of e to the 0 over 8n to the 5th plus 4n to the 3rd. Now if we plug in infinity for n, we'd get 1 over infinity, which would equal 0, which is less than 1. So the answer would be convergent. And that is the root test. Thank you.